Hi, folks. Today we're going to talk about equivalence relations. What does it mean to be equal? And here we go. What does it mean for two things to be equal? Well, with numbers, we have a fairly clear idea of what it means for two quantities to be equal. The numbers represent the same value, they're equal. But with other objects, it can be trickier. And it's important for us to actually define what it means to be equal. Are two shapes with equal side lengths equal? Are two times on different days equal? How do we even define something like December? Well, in order to do this, we're going to need equality. And before we do that, we need relations. And so before we get into equivalence relations, let's talk about what relations are in general. Now, you may remember from Algebra 2 that you are introduced to the idea of relations. The idea here is very similar, but now it's just framed from a set theory perspective. And so let S be a set and let A and B be elements of S. The ordered pair AB is the set containing A, set containing A comma B. The element A is called the first term, and the element B is called the second term. You may be familiar. Yeah, we already talked about this. This is the same idea, just from a set theory approach. And so here's the theorem. Let AB and CD be two ordered pairs. Then AB is equal to CD if and only if A is equal to C and B is equal to D. And so if we are going to state that things are equal, they have to have the same values in both the X and Y values. Sets themselves do not have orders, and so this definition gives us a way to create an order. There might be some hangups if we're dealing with the same value repeated twice, but we can deal with that later. In set theory, AB equals BA since they have the same value. So it's important to note that AB is generally not the same as BA if we're talking about ordered pairs. The order matters when we're talking about ordered pairs. Oops, let's try that again. There we go. And so a relation is a collection of ordered pairs. That's how we defined it in algebra. The collection of first terms of all the ordered pairs is called the domain. And the collection of second terms of all the ordered pairs of a relation is called the range. The domain and range do not have to be from the same set. If they are from the same set A, then we call it a relation on A. More often, we have to use a Cartesian product. And so the Cartesian product of two sets A and B is a relation which includes all possible relations with domain A and range B. The Cartesian product is denoted A cross B. Basically, take all of the elements from A and all of the elements from B and make all possible ordered pairs using X values from A and Y values from B. If elements of A are in the domain and elements of B are in the range, we say that this is a relation from A to B. Any relation which goes from A to B is a subset of the Cartesian product. Let's do some examples. And so let's let A be 1, 2, 3, and B be 11, 12, 13. Then the Cartesian product, A cross B, includes 9 elements. So we've got 1 and 11, 1 and 12, 1 and 13, 2 and 11, 2 and 12, 2 and 13, 3 and 11, 3 and 12, 3 and 13. And so those are all 9 possible elements. And the Cartesian product is the set which contains all 9 of those elements. Now let's say that R is a relation which takes elements of A and adds 10. And so 1 plus 10 is 11. 2 plus 10 is 12. 3 plus 10 is 13. And so our relation is just going to have these 3 values. The domain is 1, 2, 3. The range is 11, 12, 13. And this set R with 3 different values in it, 3 different ordered pairs in it, is a subset of the Cartesian product. Any relation is always going to be a subset of the Cartesian product. Let's check out this one. Let C be A, E, I, O, U, and let D be E, F, G. The Cartesian product C cross D includes 15 elements. We have AE, AF, AG, EE, EF, EG, IE, IF, IG, OE, OF, OG, UE, UF, UG. It's a lot of different elements, but 15 in total. If we let R be AE, EF, IG, OE, OF, OG, and UE, this is still just an example of a relation. It's just some subset of the Cartesian product. In this case, we have 1, 2, 3, 4, 5, 6, 7 different ordered pairs. Yeah. A relation can have repeated domain elements and range elements. That does not matter. And it's just a subset of the Cartesian product. We also have the idea of the inverse relation. And so let R be a relation, then the inverse relation, R negative 1, is the set of ordered pairs to which x comma y belongs if and only if y comma x is an element of R. And so we're basically switching the domain and the range, and then we're flipping all of the first and second values to create our new set. And so in short, it switches the first term and second term in each ordered pair. If R is in A cross B, then R inverse is in B cross A. If R is a relation on A, then so is R inverse. Okay. A relation on A is said to be symmetric if R and R inverse are exactly the same. Doesn't happen that often, but when it does, there's a lot of interesting facts that we can figure out. Here's a couple examples. So suppose that A is equal to 1, 2, 3. If R is a relation on A given by 1, 2, 1, 3, 2, 1, 3, 1, then the inverse relation is R inverse, and it's just switching all the values. So it's going to be 2, 1, 3, 1, 1, 2, and 1, 3. We just switched the x and y values. This is not a symmetric relation because R is not equal to R inverse. Looking at this, we have, maybe it is. Let's take a look. We have 1, 2, we have 1, 2, we have 1, 3, and 1, 3. We have 3, 1, and 3, 1. We have 2, 1, and 2, 1. This might be a symmetric relation because R and R inverse are in fact the same thing. That's a typo there. Don't get those too often. Example 2, suppose that A is equal to 1, 2, 3, and let S be equal to 1, 3, 1, 2, 2, 1, 2, 2, 3, 1. Then the inverse relation is also S, meaning it is symmetric. Now I'm curious what the difference between these two sets is. It looks like the only difference is the inclusion of 2, 2. But that should not make a difference. In this case, both of these are symmetric relations. Cool. Practice. So here are 3 practice problems. Let A be equal to ABC and B be equal to DEFG. For 1, list out the Cartesian product A cross B. For 2, let R be equal to AD, AE, BF, CG. What is the inverse relation? And then the last one is R symmetric? If you'd like, give it a shot. And here's the answers. So the Cartesian product, we had 3 elements here and 4 elements here, which means we're going to have a total of 12 elements. AD, AE, AF, AG, BD, BE, BF, BG, CD, CE, CF, CG. For this one, let R be equal to AD, AE, BF, CG. Well, the inverse, we're just going to flip them. It's going to go DA, EA, FB, and GC. Note that while R went from A to B, the inverse is going from B to A. Is R symmetric? Very not. The domain and the range aren't even the same values. And so in this case, it is not symmetric. With these tools, we can now define equivalence relations. And so equivalence relations are a way of defining when things are equal. And we say that a relation is an equivalence relation if it satisfies three properties. And so let A be a non-empty set and R be a relation on A. Then the relation R is reflexive on A, provided that for every x, we have x comma x is a part of our relation. And so we have to have the value and itself included in our relation. The relation is symmetric, provided that if x comma y is in R, then y comma x must also be in R. The relation R is transitive, provided that if xy is in R and yz is in R, then xz must also be in R. And so in this case, if we have these two, then the x and the z value must also be a relation. A relation R is called an equivalence relation if it is reflexive, symmetric, and transitive. Here is an example. Let A be ABCD, and let R be given by AAAB, BABB, CCDD. And so in this case, is it reflexive? Well, we would need to have AA, BB, CC, and DD. And we do. And so it is reflexive. Is it symmetric? Well, we have an AB. And so in order to be reflexive, or sorry, in order to be symmetric, we would also have to have a BA, which we have. All of the others are just reflexive, and so we don't have to worry about them. And the last one is transitivity. Well, with this one, if we look at it, we have the AA and AB. So if A goes to A, then A goes to B, well, that would mean A is going to B. That's included in the set, AB. If we have B going to A, and then A going to B, that gives us BB. If we did A to A and B to B, those wouldn't be going together because A turns into A, and then, well, we can't just jump straight to B. We would have to turn it into one using like this, A to A to B. And so we don't really have to worry about the transitivity property. It's satisfied as well. Since all three of these are satisfied, this is an equivalence relation. Might be weird to look at, but the way that I generally think about it is when you look at this, if we think of this as equality, this is saying A is equal to A is equal to B is equal to A, and B is equal to B. And so in this case, A and B are the exact same thing all the way through. This is just stating all of the different ways in which A is equal to B. Then C is equal to C, and D is equal to D. And so this is satisfying our equivalence relation definition. We're just saying A is equal to B, C and D are their own independent things. Here's a couple more examples, which will hopefully help illuminate this. And so same idea, A is equal to ABCD, but now we're going to say R is equal to AA, AB, BA, CC, and DD. In this case, it is not reflexive because we do not have BB. And so B is equal to B. For this to be an equivalence relation, we would need to have BB be included in here. It is symmetric because AB and BA are mirroring each other. But this relation is not transitive because BA and AB are included. And so B turns to A turns to B. We should have BB in here, but we don't. And so this is not an equivalence relation because it's failing two of the properties that are needed. Essentially, this would be like saying A is equal to A is equal to B is equal to A, but B is not equal to B. Well, you can't have that. If A is equal to B and B is equal to A, then B's got to be equal to B. You can't say that something isn't equal to itself and have itself be an equivalence relation. For this example, A, B, C, D, we got A, B, B, C, C, D, D, and then we have AB, but we do not have BA. Because of that, it does not satisfy the symmetric requirement. It doesn't satisfy the symmetry property. And so since it includes AB, we would need to include BA also for this to be an equivalence relation. With this idea of equivalence relations, and what this is all leading to is the idea of equivalence classes. How do we define when things are equal? And we define things as being equal in terms of these equivalence classes. And so let S be a set with element X, and let R be an equivalence relation on S. We define the equivalence class of X, written X in brackets, to be the set of values Y in Z or in S, such that XY is an element of R. We can say that two values which are in the same equivalence class are equivalent. And so consider the example from before. AB, BA, BB, CC, DD. This set has three equivalence classes. We have the equivalence class of A, which includes anything with A or B in it. We have the equivalence class of C, and we have the equivalence class of D. Essentially, this is saying A is equal to B, and then C and D are their own independent thing. Let's start applying this and see if a concrete example might make it a little easier to understand. And so let S be the 24-hour marks of a day. And so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 a.m. And then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 p.m. And so that means that there are 24 different elements in this set. We are going to let R, which is a relation, be the pairings of times where the hour hand on a clock matches up. And so this is going to have 48 elements. You'll have 12 a.m. with 12 a.m., 12 a.m. and 12 p.m., 12 p.m. and 12 a.m., and 12 p.m. and 12 p.m. At all of those, it's just going to be facing directly up. And so at 12 a.m. or 12 p.m., it is going to be pointed towards the 12. Then we have the 1 a.m. and 1 p.m. And so 1 a.m., 1 p.m., it doesn't matter. It's pointed towards the 1. And then 2 a.m., 2 p.m., they're pointed towards the 2. 3 a.m., 3 p.m., they're pointed towards the 3. Well, this collection of pairings is reflexive, symmetric, and transitive, and so it forms an equivalence relation. And this equivalence relation is going to have 12 different equivalence classes, which we usually refer to as o'clock. And so 1 a.m. or 1 p.m., that's 1 o'clock. 2 a.m. or 2 p.m., that's 2 o'clock. 3 a.m. or 3 p.m., that's 3 o'clock. And we can do that for all of the different positions on a clock. And so this is an example of a set which has 24 elements and has 12 equivalence classes. Another example is months. And so let S be the set of days of the year. And so January 1st all the way through December 31st. If you want to include a leap year, go for it. Doesn't matter too much in the context of this problem. And so let R be the set of all pairs of dates which are in the same month. So January 1st and January 1st, January 1st and January 2nd, January 1st and January 3rd, January 1st and January 4th, all the way through. And then we can do February 1st and February 2nd, February 1st, February 3rd, and so on, all the way through December 31st. There are a lot of elements in this relation R. R is an equivalence relation that satisfies the three requirements. And the equivalence classes would just be the month. And so if you are talking about January, well, commonly we know January to mean that you are dealing with a day which is in January. If you're talking about December, we are talking about a day which is in December. And we can define that in terms of an equivalence class. You may be noticing that this new definition of equivalence class gives us a way to classify things. And that's really what it's all about. We can say that things are equal provided they are in the same equivalence classes. And so, for instance, if we are talking about different breeds of dog, we can say that our two dogs, which are both Shelties, would be equivalent because they're both in the Sheltie category. We can also do this with things that have infinite sets. And so let's go back to numbers. Let S be the set of integers, and let xy be any pairings of numbers such that x minus y is divisible by 3. There are a lot of things that will meet this. So examples of elements in R include 6, 6, because 6 minus 6 is 0. 0 is divisible by 3. 5, 2. Well, 5 minus 2 is divisible by 3. 2, 5. 2 minus 5 is going to be negative 3, which is divisible by 3. 27, 6, negative 5, 31. There are a lot of elements, an infinite number of elements in this relation. Here's the thing, this set is reflexive. Any number minus itself is 0, which is divisible by 3. The set is symmetric. If A minus B is divisible by 3, then so is B minus A. And the set is also transitive. If we do 5 to 2, then 2 to 5, well, we're getting 5 to 5, which is definitely going to be in here. This is an equivalence relation. And this equivalence relation has 3 equivalence classes, 0, 1, and 2. So the equivalence class of 0, the equivalence class of 1, and the equivalence class of 2. If a number is divisible by 3, so that'd be like 3, 6, 9, then it is in the equivalence class of 0. If it has a remainder of 1, it's in the equivalence class of 1. If it has a remainder of 2, it's in the equivalence class of 2. For example, 5 has a remainder of 2 when divided by 3, and 5, 2 is an element of R. What we've done is we've basically created something which has the structure of the integers, but is restricted to the numbers 0, 1, and 2. This is called modular arithmetic, this idea that we can create new structures which are much more restricted but have the same properties as other sets. Modular arithmetic, it's where we take the set of integers and restrict it down to some maximum value. In this case, this would be a modular 3 system because we have 3 elements in it. We can also define equivalence in terms of geometry. And so let S be the set of all triangles, and let R be the collection of all points or all pairs of triangles which have the same 3 side lengths. And so if you are a triangle and you have the exact same side lengths, well, as you might suspect, this is an equivalence relation. We call a pair of triangles which are in the same equivalence class congruent. And so when we're talking about congruent triangles, really this is just another way of exploring equivalence, but now it's equivalence for geometric objects. We can apply this idea of equivalence to other fields as well. And so you just have to be aware of what the context is And then make sure that you're satisfying those 3 requirements. If you are, you might have an equivalence relation. Final thoughts. With numbers, we have an easy way of defining equality, but the world is far more than numbers. When we say something is December, we now have a mathematical meaning of that. And that's important because when we think about what math is all about understanding certainty, and we have to have well-defined objects in order to define certainty. Well, now we can take an abstract concept like the month of December and give it mathematical meaning. That means we can apply mathematical meaning to a broad spectrum of things, and we can apply all of our rules of set theory to just about any situation. Equivalence classes give us a way of understanding and categorizing equivalent things when we're talking about objects and relations. Much more complicated than numbers. So if we are dealing with equivalence class of fruit or not fruit, there's some fruit there. With that, I'll let you get to work exploring where you find equivalence classes in the real world. Good luck, folks.